Okay, so it's still semester 1, 2019. We've had another question and we're going to power through and talk about that. So we're interested in how to go about doing proofs even of things that are technically in the lectures. And you're asking, saying, well, how would you prove, for example, Chebyshev's inequality? Okay, so can you tell me what Chebyshev's inequality is? Oh, I know Chebyshev's inequality. Just a second. I don't know how to spell Chebyshev, but I'm presuming it's this. So Chebyshev's inequality says that the probability that x is greater than or equal to k standard deviations from the mean is less than or equal to 1 over k squared. Okay, yes. Okay. All right. Okay. So I presume the proof of Chebyshev's inequality would be different depending on whether it was a discrete or a continuous distribution. So let's do continuous, or would you prefer discrete? Continuous. Okay. Okay. Well, this is going to be an exercise in what would David do, or what could you do to try and figure out a proof from scratch. Presumably your lecturer would normally give you a hint of some sort. Now I don't know what sort of hint that she might give, but I can probably abstract that from the process as we go along. So first I just want to think about what the hell is going on here. We have a continuous distribution x. It has whatever distribution it has, and that's my f of x. And maybe the mean is, say, looks like it's about here. And so if we mark out standard deviations, and then we're saying that the probability out here is less than 1 over k squared. That's what we're saying. This one would be less than 1 over 9. The probability out here would be less than 1 over 4. The probability out here would be less than 1 over 1, which is great. Can deal with that. Okay, so the k sort of has to be greater than 1 for this to make any sense. All right. Cool. Okay. I have a feeling that this might utilise one of the other inequalities in order to prove it. No? All right. Well, let me just be extremely naive and see what happens, right? That's 1 minus the probability that would be that. Seems reasonable to me, a little easier for me to do a proof for the inside. This is the outside, to do a proof for the inside, because the inside would be an integral from a specific place to another specific place. But the outside would be two different integrals, one from here to infinity and one from minus infinity up to here. So it should be easier to do something that's a defined area. And this would be the same as k is between mu minus x is between these things. So presumably that's what I would do. I mean, I don't know if this is useful, but this is what it is. Okay. Well, right. So somehow there's a k squared in here. And I need actually this whole thing to come out to 1 over k squared, which means this bit here is going to have to come out to 1 minus 1 over k squared. So just a second, we want... I mean, that's what we need, because we need this whole answer here to be 1 over k squared. So if this was 1 minus 1 over k squared, the minus 1s would cancel out. Does that help me? Dunno. Just thinking about what I have to do. Okay. Not really sure where to go here without having seen this proof before. Did the lecturer show this proof? Oh, interesting. Oh, okay. Ooh. So that sigma, we could figure out what the sigma is. It'd be useful to know what the x and what the mu and the sigma were. Maybe. Okay. So let's see. This mu would be the integral. That's what mu is. And that's what sigma is. Well, sigma squared anyway.
Yeah, so she sort of just goes from there.
Yeah, don't.
So I won't give you the punchline.
Okay, so just a second. This thing might possibly be related to this thing. Right. Almost there. Not quite. But if this went from mu minus k sigma up to mu plus k sigma, then we might be able to show that that's less than or equal to something. Yeah. Okay. This is certainly greater than or equal to this. Right, because I'm integrating the entire real line. If I'm only integrating this bit, then that would be smaller. Okay. So I could do a substitution, couldn't I? Because that would neatly make my x minus mu go away, I'm reckoning. Be 1, and we also have that x equals mu minus k sigma would become x equals mu plus k sigma would become u equals k sigma, and so I'd get that sigma squared would be greater than or equal to oh crap, that's going to be u plus, that's not helpful. Okay. But of course f is, oh crap, that's a greater than. I was going to say f is less than 1. It's not less than 1, but it's certainly positive. There's a Swifty being pulled here. So we need to get it to here, really. Unless I should have gone less than or equal to. No, I really need to see this proof. I think that it might take me a little while, but just bear with me for a minute. The cumulative, the ordinary distribution function doesn't have to be less than 1, does it? Because it's how quickly like you just need the area to be less than 1. And so it can go above 1 if the other bits are below 1. Okay, that's fine. I mean, it must be a reasoning to do with the sizes of these numbers involved. I mean, I could try and work backwards a little further from what I've got. I mean, because I don't want to actually show that this is equal to 1 minus k squared. I want to show that I don't need to show that it's equal to that at all, do I? I need to show that if this has to be less than or equal to 1 minus k squared, I need this to be greater than or equal to 1 minus, right. Well, these are still equals, that's okay. Because if this is greater than this, then this will be smaller than 1 minus that, right? All right, give me some of the punchline.
So what she's done is taken the integral from minus infinity of the variance as you had before, and then just split it up into three different variants. So minus infinity to sigma minus k squared to plus k squared, and then plus k squared to positive infinity.
So like what I did here?
Yeah.
And then we dropped this integral.
Sorry?
And then we dropped
Oh, we dropped this one. Okay, cool, that's fine. So just a second. Let's try that again. So this was interesting because I was wondering as well whether I shouldn't go greater than but instead go less than something. So you're, okay. And so we're saying, so when we drop so we're going to remove the bit in the middle. Okay. And so that's going to be still greater than or equal to mu, wrong thing, mu minus k sigma and mu plus k sigma. Okay. Sure. Then what do you do?
So we know that x is going to be always less than mu minus k sigma in the first integral.
Mm-hmm.
And we can change the boundaries. Like, we can kind of approximate this x minus mu squared as the highest boundary.
Ah. So
Sigma
Doesn't make any sense to me, I'm sorry.
Come over if you want.
Yeah.
So just 1 minus mu.
Okay. So we're going greater than. So we still are definitely aiming to have this integral, but maybe not this one, maybe the two outside bits separately. Okay. All right. So let's see. Since let's look at this one, these x's are above mu plus k sigma, then x minus mu is greater than k sigma. And so therefore this integral is greater than the integral of just k sigma. Oh, cool! Okay. So for the first integral, x is less than mu minus k sigma, which means x minus mu is less than minus k sigma, which means that x minus mu squared has to be greater than k squared sigma squared. So basically we're saying that if you have a big negative number, it has to be bigger than the square of the other ones. And for the second integral, x minus mu squared is also greater than or equal to k squared sigma by similar reasoning. Okay, good, good, good. And so therefore sigma squared has to be greater than or equal to this. Just copying what I had before so that I can rewrite it. If I was in the exam book, I wouldn't have to copy it. Okay, so this is greater than or equal to that, and so therefore the integral of it has to be greater than or equal to and this is greater than or equal to k squared sigma squared, so the integral of it has to be greater than as well. Which I guess technically only works because the f of x is positive. If the f of x is negative, the greater thans and less thans would be all ruined. So that's k squared sigma squared and so that would be, therefore, the probability that x is outside of, that's a plus, yeah. X is less than mu minus k sigma, plus the probability that x is greater than mu plus k sigma. That. Which is the same as the probability that x minus mu is greater than k sigma. Right. So, summing that up, we have that k squared sigma squared p is less than or equal to sigma squared, and so therefore p right, dividing both sides by sigma squared and k squared. Okay, so I went down the wrong road to begin with, and I might possibly have, given enough time, gone back and said maybe this wasn't the best approach, because I thought that would be easier. Right. I'm not sure what sort of hint she would give, other than possibly if I think probably the key thing to maybe give would be to tell you to think about this, and you'd have to figure out how to work that in somehow. She might even, if I was writing it, I might even give hint, first show that sigma squared is greater than or equal to these two integrals. Not these ones, but with the k squared sigma squared in it. Yeah. Okay. So, yeah, I know. So the choices I had at this point, like I did something where I removed, I thought, well maybe, so it seems not too illogical to try and write down the definitions of what sigma and mu are and try and reuse them. And when I did it, I went, well, I compared it to the thing that I had split up, but maybe I should have been much more naive and thought about these two integrals directly. And I guess a hint that there was an k squared here means that somewhere along the way we have to square something. Do you know what it was? Yeah, could have gotten there directly from... I just want to see if I could get there, reconstruct getting there directly if I was ever asked to prove Chebyshev's theorem. So, yeah, that's where I'd start, I reckon. The absolute value, just square both sides because they mean the same thing. And then I would go, oh look, that's the variance. This is totally in the variance. And so I would start to go, because this probability I know what that probability is, but I might start thinking about that. I might start going, yeah, no, that's bad. But this would give me the hint that I should use the variance if I did that first. So if I was trying to remember this proof, I would go, I'll square it, and that will remind me that I have to use the variance. Yep. And so then I would go, okay, well, what I really want to do is be interested in this being greater than or equal to k squared, sigma squared, like, or less than. Yep. Cool. Right. Huh. So this is... So that's cool. This is less than or equal to the integral of the part of the line where this is true. So you have the whole real line, right? And in some of the... In some parts of the line, this is true, and in some parts it's not true. So this is where x minus mu squared is less than k squared sigma squared, and out here this is where x minus mu squared is greater than or equal to k squared sigma squared. So this integral is greater than or equal to the integral on just the part of the real line I want, which is this bit. So that's just in my head. Where R is the part of the real line where x minus mu squared is greater than or equal to k squared sigma squared. Like this is what this region here is, R. Yeah, that's cool. I love it. Okay, where R is that part of the real line. And if R is part of that real line, this minus mu squared is greater than k squared sigma squared. But when you integrate over a region, it's the same as the probability of that region happening. So that's which is that. And so therefore I guess I should put a reason in there just a second. Integral of f of x over region R is the probability of R happening. Well, maybe not happening, just the probability of R. I love this version of the proof. Go, well, I like saying we're going to integrate over the region where that happens. And if this is the region where that happens, then this is greater than or equal to k squared at sigma squared. That's sweet. This would be so fast in the exam if it was in there. I so want another proof where I can reuse this idea, but I don't think I'm ever going to get one. Cool. I'm not sure what sort of hint that she would give that would make us feel like we had done this before. But now that I've done it 2 ways, I can remember this within a week from now. So I could redo this in an exam. Okay. Since I'm here, are there any other proofs that you weren't sure on how you might deal with? Because some of them I'm better at than this one. I reckon some of these ones are, the reason there's a name on them is that not many other people thought of it, so they're not that easy to come up with on your own. Yes?
Oh, that's quick.
Oh, the one with Markov's inequality in the past exam?
It's a sample exam, actually.
So you are interested in how you could come up with this from scratch?
Yeah, just those that I'm not quite sure how.
All right, let's go. Okay. So Markov's inequality is the probability that y is greater than or equal to a is less than or equal to the expected value of y over a. Okay. but for a discrete distribution with values 0, 1, 2 up to n. Okay. Cool? Sure. Okay, I'm not going to look at the solution, I'm going to see if I can come up with it. So it seems to me it would be useful to think about what the expected value is. So the expected value of y would be the sum of y times the probability that y is equal to y. Okay. And I guess the probability that y is greater than or equal to a would be the sum from y equals a up to n of probability that y is equal to y. Just writing down the definition of the two things that I've got. So, if y is greater than or equal to a, if I'm only interested in those ones, then this y will be greater than or equal to a. So I'm thinking that if I split this up into the part where it's, because this one only involves a bit where it starts at a, if I split this into the part that's less than a and the part that's more than a, that might help. Okay. So we're going to note these things, and then we're going to say the expected value of y. I'm just going to start again if that's okay. And that's going to be from 0 up to a minus 1 plus the bit from y equals a to n, like that. Now let me just have a look. The part of my equation that has ey in it has to be greater than or equal to the other bit. So I would like to stick a greater than or equal to sign in here, because of the part that it's in, it's pointing that way. So this is totally going to be greater than or equal to just this bit. Okay, I can definitely do that because this thing is not negative. That's greater than or equal to 0 for all y. Doesn't really matter what they are. And it was very useful for your lecturer to indicate that the values of y can't be negative, so they start at 0. So y is this. So if you've got something positive, when you remove it, the answer gets smaller. So in my head it's like, that's what I was thinking. If I remove something positive, the answer gets smaller. Okay. So I'm going to need to somehow connect up into this probability of y being greater than or equal to a. So in somehow I'm going to have to get rid of this y. So, well, I can't get rid of it, but I do know that if y is from a to n, this y is greater than or equal to a. And so this thing is going to be greater than or equal to what I get when I just make them all a. Since y is a greater than or equal to a for everything that's part of this sum. And now I can pull out the a. So it was a very similar trick to what happened in Chebyshev's inequality, where I said, well, it's greater than or equal to this thing, and then I can pull that thing out of the integral. So the expected value of y is greater than or equal to a. Oh, well, not quite there yet, just a second. And this is totally the probability that y is greater than or equal to a. Because we wrote that down earlier, just here. So the expected value of y... Oh, it's not an infinity. They're n's. Sorry. It wouldn't make any difference if it was an infinity anyway. That's all right. Probably that y is greater than a. Did she give a hint? Oh, she just said use the definition of the expected value of y. Okay. Well, my natural instinct is to write down the definition anyway, so that was useful. Okay. So what was it that I did that made sense of what was this? The first thing I did was try and write down the definitions of what these things were, because that would make useful sense. And then I thought, well, there was no particular reason I started at EY, except that it's easier. I know it's easier to try and make things less complicated than it is to make them more complicated. And so I thought I'd start with this one. And I also knew that this one used more n's than this one, more values of y than this one did, so it'd be easier to remove pieces from it than add pieces to it. So that's why I started here and split it up into the bit that matched what I was aiming for and the bit that didn't. And then I went, well, I can always just leave out anything that's positive. And then I can always, well, I don't know, it was just an inspiration that I needed to get to here and somehow therefore remove the variables y. So if I make them all the same, it'll be easier. And after that, it just sort of happened. Okay. Cool. So the only other proofs that sort of come up are ones where they're not really proofs per se, but it's like where you're using like moment generating functions and crap, and you have to use your knowledge of infinite and finite sums. So there's a revision seminar about that already, I think, on the website, just about the various sums that you had to use along the way. And the classics were the binomial theorem and e to the x is Taylor series that we had to keep using. But I can't think of any examples off the top of my head at the moment. And there's ones with manipulating, I don't know, does your lecturer get you to prove things like, did your lecturer get you to prove this? Prove that sort of thing? How do you feel about that proof? You all right?
Yeah, I'm fine with it.
Okay, cool. Just making sure. Yeah, I have to remind myself of this one every time.
It's in the bivariable. Use that conditional. Yeah, okay.
Because the proof is different depending on whether it's continuous or discrete, but it's pretty similar. Yeah, basically, but that thing. It's the expected value of x squared minus the expected value of x whole squared. Yeah? So, yeah, okay. Cool. I was just wondering, just thinking of other proofs that might happen. This proof is different depending on whether it's a discrete or continuous distribution, but they're fairly similar actually. Yeah. Cool. That's okay. And this was used in a proof in a past exam, was it? To do something else?
Yeah, question 6.
For two random variables, y1 and y2, it can be shown that the expected value of y1 is the expected value of the expected value of y1 and y2. Using the above result to prove for random variables y1 and y2 that the variance of y1 is that. Okay, let's go. I'm just going to... For y1 and y2, the variance of y1 is the expected value of the variance of y1, y2 plus the variance of the expected value of y1 given y2. Sure. Great. Okay. Well, variance of y1 would be the expected value of y1 squared minus the expected value of y1 squared. I don't know if that's going to help, but that's a useful thing to start with. And, okay. It might be easier to start here. So I just want to see what does it even mean? So this is saying that y1 given y2 is a random variable of its own that has a variance. And that variance would be based on what the values of y2 are. Because y1 is a constant given y2, so this would be based on the values of y2. And the expected value of y1 given y2 is a random variable based on what the value of y2 is. Okay? Well, if I'm supposed to be using this other fact, that's what that would be. And I guess this would be y1 given y2. I suppose, like the expected value of anything is the expected value of the expected value of that thing given something else. And then, alright, well this would be pretty close to the variance of y1 given y2, I reckon. Just a second. The variance of y1 given y2 would be the expected value of y1 squared given y2 minus the expected value of y1 given y2 squared. Are we allowed to just use that rule? Seems reasonable to me. Okay. Cool. So the expected value of this would be the expected value of this minus the expected value of that. Damn it. Too many brackets. Okay, so put that over there and then write it backwards would be this. And so then if I do the expected value of that, get the expected value of the variance of y1 given y2 plus the expected value of y1 given y2 squared, because expected values can expand out over plus. Okay. So therefore the variance of y1 is coming out to this thing instead of that. Damn it. Right. That thing. And this thing here is apparently the variance of the expected value of y1 given y2. Which it is, because it's the expected value of thing squared minus the expected value of thing all squared. Right. Cool. Just to be clear, this thing is in both of those positions using that rule about how variances work. So I used often the rule that the expected value of the variance of x is the expected value of x squared minus the expected value of x squared. Okay. Right. But you'll notice something that I did there. I made a start, and then I thought, well, I recognise this as part of something else, so let me figure out that other thing, and then I can use it when I get there. So it's okay to leave your normal line of working temporarily to do some other stuff for a while. Yep.
So where did that variance of y1 on top of that page?
Where?
So on the top of the other page. Where did you get that first term from?
This bit?
y1. No, like where is that coming from?
Where's the?
No, variance of y1.
Yep.
Why is it that equal to those three terms?
Oh, those three things?
Yeah.
That's because I took from here, I shall call this one 1, and then I will say I'll sub this thing into 1. So I took this thing, and I found what e of y squared, y1 squared given y2 was, which was this. So I found what this came out to, which is this, and I subbed that in there, and it produced this. Yeah. So worthy point. If you do leave your working and come back to it later, it's not the worst thing to label it like this. Yeah. Cool. So that the person reading it can tell where you got this from. Cool. All right. I think I've done another one on counting stuff, another revision seminar, which might have some other examples. I can't remember. Though if people watch this video first, it won't make any sense. But in the other video, we asked about counting techniques. Yeah, I hope that strategy is enough to get you a little further. Yeah. Okay. Well, I think that's quite enough.